Welcome back. So today we're going to continue talking about Bayesian inference, and we're going to continue focusing on models that have some kind of convex geometry property, but we're going to bypass using Markov chain Monte Carlo. So yesterday we saw that we are in a setting where we want to estimate an unknown image x that we'll assume to live in a very large Euclidean space, and that we don't observe x, we observe y, and y is related to x by a mathematical model. And we said that because we are interested in going beyond point estimation, so we might want to make statements about our model or about our x, such as confidence intervals or hypothesis tests or model selection or things like that, then it makes sense to use a statistical model to relate x to y, because, well, we discussed a number of benefits in doing this. And we also said that we're in a setting where usually y doesn't have enough information to recover x reliably. So there's a lot of uncertainty about x even after measuring y. So for example, if y is related to x by this simple linear model, which is sometimes a quite good model and sometimes just a first order approximation, then if the operator a, for instance, is rank deficient, then clearly we can't recover x from y reliably unless we bring some other form of information into the game. And we said, well, we do this by regularizing, and in the Bayesian setting we regularize by using our prior knowledge, which we introduce formally in the form of a statistical model for x. So this is the marginal distribution of x, the distribution of x on its own, regardless of the value of y. And then we apply Bayes' theorem, which is this formula here, and what we get is this conditional distribution, the posterior of x given y. And we said that this is a very nice mathematical object because it models our uncertainty or our knowledge about x after measuring y, taking into account the prior knowledge that we had, that we encoded into the model. And I'll stress model. So this is a representation, and it's very common, and this also happened to me, that when you are a student and you learn about Bayesian inference within the mathematical imaging community or any community that is close to electronic engineering or things like that, you forget that this is a model and you start having arguments about the validity of things. And that's not the right way to approach it in my view. X does not come from P of x. P of x is an equation that you write down. Nature does not follow equations that you write down. But you need to make sense of nature. So you will write down a mathematical model because mathematical models are things you can manipulate following rules. And if you follow your rules correctly, then you know that your conclusions are mathematically correct. And when you finish doing that and you obtain a model P of x given y, then you need to step back and say, well, are these conclusions, mathematical conclusions, valid in the real world? Well, they are approximations. So you step back and you say, well, if all my math is correct, then I started making some approximation of the real world, and now I obtain another approximation of the real world. So this is my model. And in this talk, we'll focus on models that have this shape. So exponential of minus a convex potential function. So we call these models that log-concave. And this was also the focus of my second talk yesterday. And we did sampling for those models, Monte Carlo sampling. But we also said that people usually don't do Monte Carlo sampling. They do maximum-a-posteriori estimation. So they just go for the minimum of this function. And this is because until now we've mainly used the Bayesian framework just to write down a model and then derive a solution for the imaging problem. But we still address the imaging problem as if we were not proper Bayesian statisticians. We just think of the solution as an image that we'll display. And this is not a full paradigm shift. This is sort of like halfway. We're only using the model to derive an estimator, and then we go like, this is the solution, and that's it. Now you take it as if this was the truth. And then the clinician will look at the solution and will go like, I see this, I see that. And that's not a full paradigm shift, because what we should be trying to do is say, well, you want to know if the tumor has grown or not. Or you want to know if this specific radiotherapy treatment is going to be effective or not. Or you want to know if that specific galaxy that we see in the sky has an energy level that is within this bounds or not. And your analysis should go all the way there. It shouldn't stop at, this is the image, now you figure out what to do with it. So if my model is log-concave, so if this is convex, then I can compute this very efficiently by convex optimization. But there's a number of things I cannot do just by computing this. I cannot have a nice description of the uncertainty about x. I have just one point that I display. But I don't know what are the specific aspects in this solution that I can trust. I also don't have good theory for how this is behaving as a Bayesian estimator. So yesterday we said, and we'll revisit this, that Bayesian estimators don't arise by just someone postulating, this is my estimator. I minimize this cost function, this is my estimator, full stop. That's how they arise in other areas, like in variational analysis. In Bayesian statistics, they arrive from Bayesian decision theory. So you have to tell me, this is how I want to measure estimation error. And then Bayesian decision theory says, well, the optimal estimator, the Bayesian estimator, for that way of measuring statistical error is this one. Here we're not doing that. We're just going for the maximizer of our density, and we're declaring this is my estimator. But it's not very clear why this is a good estimator. What are its optimality properties? What are you summarizing? And finally, we also said that this kind of approach struggles when you have unknown parameters in your model other than x. So if regularization parameters are a classic example of parameters for which we don't have a good value a priori, and that make us struggle. So what I said yesterday was that these three things are some of the things I call my elephants. So big problems or big gaps in the imaging literature that we have somehow managed to avoid so far, largely. I mean, there are some very good papers on these topics, of course, but if you look at the body of work that we produce every year, you'll see lots of papers that, for instance, improve a bit on how we minimize this function, improve on our guarantees, improve on the convergence rates. So there's a lot of very clever people working on that, and we have a fantastic toolbox of methods. But when it comes to, well, how can I analyze the uncertainty about x, then you don't find many interesting things. And clearly the rate at which we produce knowledge is much slower. And again, this was true when I did my PhD. So I finished 6 years ago, and it's still true now, and I think it was true 10 years before I did my PhD. You want to compute the minimizer, you have a regularization parameter, you're not sure of how you're going to set it, you try different values, you choose one, you stop there, and it's something we don't know how to do very well, and we keep working on other things without addressing that problem. We keep developing better methods to minimize functions, or better methods to produce a nice image, provided that this parameter is chosen correctly. But we don't address the fact that we don't know how to choose the parameter correctly unless we're in a very controlled setting. So we illustrated this with one specific, with a number of examples, but this is one that we used a lot. We said, for instance, if you have this radio interferometry measurements, so these are Fourier measurements of the radio sky. Here I'm just displaying the absolute value, and we discussed that in this setting, you don't have enough Fourier measurements to do the inverse Fourier transform and recover the image, so you need to regularize your problem. We see this because this Fourier plane is full of white regions where I don't have measurements. We also said that I can't design what measurements I will acquire because they arise from the position of the stars in the sky, how the Earth moves, and where my radio antennas are. So this is not something where I can say, well, I'll do uniform sampling, or you have what you have. And we regularized the problem using an L1 prior on a wavelet representation that is specialized for this problem. And we get really good results. So we get reconstruction stars that are really good. However, we see structures in the image, and it's very difficult to quantify the uncertainty on these structures. So this is in logarithmic scale. It has a huge dynamic range. Am I really sure that there is a structure there? Wouldn't it be possible to do another reconstruction of those Fourier coefficients that would not give me this? I mean, if I remove this, what's the change in the Fourier coefficients? Maybe it's minimum. Maybe this comes from my algorithm hallucinating the value of the other Fourier coefficients, like Daniel said on Monday, and it's not a real feature. And then in any case, even if it was a real feature, because radio interferometric images are usually acquired to do physics, people doing physics want confidence intervals because they see this image as a physical measurement. It's not an image they want to display. They want to do science with it, and when they want to do science with it, they need error bars on their quantities. And we have not been very good at providing them with the tools they need to do things like put error bars on an image structure. So yesterday we saw some ways of doing this by using MCMC. Today we'll revisit this without using MCMC. And the hope is that I will persuade people to start doing this by just using optimization, because that's the tools they like to use. And once they have been partially evangelized into Bayesianism, then they will start doing MCMC. So that's the goal of any Bayesian statistician: evangelize the audience so that they all become Bayesian statisticians. So where does the posterior probability mass of X lie? So we talked about this yesterday as well. I'm not trying to report one solution. What I want to understand is what's the part of my space of solutions of images where most good solutions live. So we formally write that as a set C alpha, such that the probability of X belonging to C alpha given the data I observed is 99%, 95%. And we said there's an infinite number of ways of slicing the parameter space to get a set that covers 99% probability. But there's one that is good in many ways. It is optimal in a decision theoretic sense. It's also practical because I can write it down, which is the high posterior density region. And that's just taking your cost function and slicing it at a certain level. So if my cost function to compute the map estimator looks like this, what this says is that any value that is below gamma of alpha defines what I'll call C alpha star. So that's my set of solutions. And the gamma level has to be chosen such that the probability of X having a cost that is below gamma of alpha is 99%. So with MCMC, it's easy to compute this. I had a chat with one of you yesterday about how you would do it. I'll put some code on my webpage later to show you that it's, I mean, unless you're going for a very small value of alpha, if you go for like 1%, you can compute this quite easily. So we could estimate it by MCMC, but in high-dimensional models, this is not necessary. And it's not necessary because there's something very acute happening, a concentration phenomenon. So here I have two samples, two trajectories of my MCMC algorithm, and it starts from two different places, and each sample is an image. And what I'm displaying here is the value of the log posterior density of that image. So I'm displaying actually the value of phi, my cost function. And I see something very strange. My MCMC algorithm is stabilizing at a value of phi. And this shouldn't be happening because this is not an optimization algorithm. I'm not minimizing a cost function or maximizing a cost function and then, okay, I reach the maximum, I stay there. This is an algorithm that is dancing around the space of images. And it reaches an equilibrium point. in terms of the density of those samples, but the samples are all the time changing. They're becoming different images and exploring the parameter space. It shouldn't be becoming stable. In fact, what's happening is that they are exploring the space according to the distribution, but the probability that one of those samples from this distribution has a value of phi that is far from the expectation of phi is very small. So what happens is that when your probability distribution, so when your random vector becomes very high dimensional, very, very high dimensional, although it can take value anywhere in the space, it concentrates on the surface of a body of dimension d-1. So it's as if, for instance, I had a football ball and my samples would stay on the surface of the ball instead of exploring all space. And this is the correct behavior. If you take a Gaussian distribution and you blow up the dimension, the probability that a random sample from that Gaussian distribution is far from the surface of the ball becomes very, very small. This is known as a concentration phenomenon. And it turns out that all log-concave distributions, so all distributions for which phi is a convex function, have a concentration phenomenon. This is something that I discovered by doing the MCMC sample, discovered in the sense that I became aware of this, and then I started looking at the probability literature, and luckily for me, a probabilist had just published a paper saying that this was true. If he hadn't, then I wouldn't be giving this talk now. I would be giving a different one. But I wouldn't be able to have done any of this work. So it's an interesting example of how math will percolate. In this probabilist had no idea this would be useful for me. He just thought it was an interesting thing to study how, you know, this abstract random vectors behave when you constrain phi to being convex. So what can you do when you know that the vector will live on phi convex? Sorry, on the surface of the body for which phi is almost equal to a constant. Well, what you can start doing is manipulating your distribution without using MCMC sampling and just using the concentration properties. So what you can do, for instance, is propose this approximation to C alpha. What this approximation says is that for any posterior distribution that is log-concave, so which for phi is convex, then this set, so where I have replaced gamma of alpha by this quantity, so phi evaluated at the map, so phi evaluated at its minimum value, plus this universal constant that only depends on dimension, but that does not depend on the model, this thing contains the true C alpha. So what that tells me is that there is another threshold, I'll do in blue, that I'll call gamma tilde alpha. What I'm saying is the set defined by gamma tilde alpha, given by this explicit expression that is trivial to evaluate once you have X map, this set contains the other one. So this is a set that defines a credible region, an HPD region, with an alpha that is a bit smaller than the alpha you're going for. So if you wanted 5%, well, this one will cover, so if you wanted a 95% region, this one will cover at least 95% of the space, or a bit more. So if I want to do, for instance, a hypothesis test, then what I can say is, well, if X does not belong to C alpha tilde, then it does not belong to C alpha star. So this is a conservative approximation. You wanted to know that at least 95% of your solutions were there. Well, I'm giving you more than 95%. So I'm telling you, if this solution is falling here, so you're concluding that this is not a very likely solution, then you can do this directly with my approximation. You don't need to compute the exact thing because it includes the other one. And we get it for free just by solving the problem by map estimation. Well, is this a rubbish approximation or is it useful? Well, it turns out it is useful. So what I can show is that the difference between this threshold and the correct threshold that you have to normalize by dimension, because otherwise, as you increase the number of pixels, phi obviously increases, and then this would diverge. So as you normalize this by dimension, this lives between 0 and 1, plus a term that will die very quickly as dimension increases. So this is a stable approximation. If you look at the error per pixel, in a certain sense, as you let dimension increase, then the error always stays between 0 and 1. There is no curse of dimensionality. This will not blow up. So it's stable. And these bounds are tight asymptotically. I can find specific cases for which there is no error and specific cases for which the error is exactly 1. These are the uniform and the Laplace distributions in d dimensions. And yeah, so we can't improve them any further, but we know that they will not blow up. So what do you do once you have this kind of results? Well, you can do what we did yesterday, but without using MCMC, and hence reduce a lot your computing times. So here I have a reconstruction of a radioastronomic image where I have essentially done a pseudo-inverse by Fourier. It's like computing a Tikhonov regularized solution. So this is the dirty, what they call the dirty image, and this is the reconstruction with this specialized radioastronomy model. Yeah?
Sorry, can I interrupt and make you go back to the previous results? What's surprising is that there's nothing that depends on any convex quantity of the phi function. Is it expected, or there's no, like, any convex function, whatever it's...
Yeah, so any convex function will hold. I suspect that if I could say, well, it's strongly convex with, I don't know, a convexity constant mu, that maybe it would be possible to refine these results. But I have not done that yet. And I've not seen results in the probability literature that would make that easy. But I suspect it is possible. Because the worst case, so the worst case is uniform, I think. And in the case of uniform, if I could say, for instance, that you had Lipschitz differentiability, then I would probably be able to bring down this to a half or something close, and then improve on that way. And if I had a strong convexity constant of something, then I could rule out Laplace, and maybe I could push this to a bit over 0, get tighter bounds. So let's say I have, and yes, please do, as we said yesterday, just ask questions as we talk about the material. Don't wait until the end if you have a question now. So if you use the Bayesian model that we described yesterday, again, so this is a sort of like specialized Bayesian model, but that has many, its main ingredients are very similar to what Clarisse described. This is just a model that is in a certain way promoting sparsity or near sparsity in a wavelet representation. So then you get this map estimator that looks very nice. And then if you compute the credible intervals that we showed yesterday, so here I'm again doing scale 10 by 10, so I'm looking at structures of size 10 by 10, and I'm seeing how much I can trust the value of the image in that region for each patch of 10 by 10 in the image. And I'm essentially looking at how large the confidence interval is, and I'm displaying that. So black is a region that I can trust a lot, and as I move into red, green, of that, I get regions that I can trust less. I obtain this result just by using my approximation, and if I was doing the exact thing with my MCMC sampler, I would obtain this, which is very similar. And in this case, it takes a bit less than 2 seconds, and in this case it took several minutes, of the order of half an hour. And if you go out to check this paper, you'll find lots of other results at different scales with 4 different images, and we consistently find the same results. I'll have references at the end of the talk where we have other applications in medical imaging, in other fields, where we always observe very reasonable approximation errors. If we quantify them, they're usually of the order of 1–2%, something like that. Okay, so here I have another example, again a different radio galaxy, and again I have in black regions that I trust a lot, and in green and red regions that I trust less, and we get the same results as with MCMC. By the same, I mean from a practical viewpoint, they are pretty much equivalent. I wanted to revisit this sparse deconvolution example, because it's an example where I'm really pushing how much I trust my model. I have used this L1 penalty here that for this image is clearly not a very good model, but the map estimation results nevertheless are good. We said yesterday that there's a lot of debate about whether you can claim that it's good because the Bayesian model is working well, or whether it's good because something else, non-Bayesian, is happening. So if you're interested about this and you were not here yesterday, I'm happy to have that conversation again. But what I wanted to discuss today was, well, let's say I'm interested in these 3 molecules here. So we said these images are acquired because people want to know the position of the molecules. And once they know the position of the molecules, they need to put error bars on those positions. So let's say I was interested in these 3 molecules. Am I confident about their position? How much could I move a molecule and still have a good solution? So we said that in their first, in the original paper by Su that was published in Nature, I think it was Su who spent a lot of time repeating the experiment 100 times and measuring the position of molecules and doing this laboriously, and he arrived to the conclusion that there was a precision of 80 nanometers. And if we just play with our confidence region and move the molecules and see how far I can move them until I exit the confidence region, moving them in different directions, we obtain this elliptical confidence regions, or error bars, if you like. And they have roughly 90 by 140 nanometers. So it's not very different from the average precision of Su. And when we did this by MCMC, we found something that was closer to what Su had found. And in this case, essentially, what I'm making is an error of 1 additional pixel. So I'm going a bit above that. But the order of magnitude is absolutely fine. I have something that is in the range of values that Su found. And I get this very quickly. So I've acquired the image, and in a few milliseconds, I have my confidence regions. And if you change the microscope, I would still find in a few milliseconds my confidence regions, whereas Su would have to spend, again, a big part of his PhD repeating the experiment 100 times and doing the matching. And hypothesis testing. So this is something I saved for today because I really like, and I think it sits more nicely once you're doing convex optimization. So what happens when you have a structure in your image and you want to decide whether you can trust the structure or not? So let's say I have a tumor in a medical image, like the brain lesion that I was showing yesterday, and I want to decide whether it is sensible to support the claim that this lesion is there against the claim that there is no lesion. So what I will do is I'll split my parameter space in 2 regions. So this is called hypothesis testing. We discussed it briefly yesterday. It's an important topic, so we'll re-explain it today. The hypothesis test is a situation where you split your space of solutions into 2 groups, and then you assess the probability that the solution is in one of those groups as opposed to the other one. So in this case, we'll talk about images that have or don't have some feature. So in my case, let's say that I I'm interested in solutions that either have a lesion or don't have a lesion. So once I have observed my, my image, there's a specific lesion I want to test. And in principle, I should not be doing this. I should be postulating the lesion before observing the image, but in the imaging context, this would be absolutely impossible. So we are a bit cheeky and we're doing it that way. We have observed a lesion and now we're going to test a posteriori if the lesion is there or not. And so what we do is we design a set of images that look pretty much like our solution, but don't have a lesion. I'll explain how we do that in a minute. And then I'll have the rest of the solutions which do have a lesion, so there is a brain tumor. And what I want to do is say, well, is the probability of not having a lesion smaller than 1%? So if I check whether there is no tumor and the probability of no tumor is really small, then I'll conclude there probably is a tumor. So if I have a radio image and it's imaging, I don't know, the sky, and I have a model for background information, and I test whether this is background or not, then if the probability of background is really low, then I'll conclude that probably this is not background, there is something else. There is additional energy that comes from, I don't know, for instance, an airplane approaching the radar. However, calculating this probability is not straightforward. Even if I was doing MCMC sampling, I would have to check if each sample falls here or falls here, and if alpha is small, then it might take a long time to get a reliable estimate of this. And what we showed with colleagues from Edinburgh, Audrey Repetit and Yves Houillot, is that you can solve this by convex optimization in a way that is very efficient and does not require sampling. So if your set S associated with H0 does not intersect with C tilde, then the probability of H0 is smaller than alpha. And the reason is very simple. If, let's say, my set S of all images without tumor falls here, and this part accumulates 95% of the probability, then this set cannot accumulate more than 5%, because otherwise I would have more than 100% probability. So all I have to do to solve my hypothesis test is solve a convex feasibility problem, provided that I construct S such that it is convex. But if I do, then all I have to do is check if there exists a point that belongs to both S and C tilde, and if there is no such point, then I can conclude that the probability of H0 being smaller than alpha is, that H0 has probability smaller than alpha. So how do I do that? Well, I work with two images at the same time, two solutions. I force one solution to live in C tilde, and I force the other solution to live in S. And then I minimize the distance between the two. So you algorithmically do this by projecting, like trying to minimize both, and at the same time projecting them both on their sets iteratively, and this will find your C bar and C under bar. And if it turns out that they are very, very close to each other, so numerically they touch each other, then you go like, well, these two sets are not disjoint. And you have just found a counterexample. You can say, look, this point here, it's in a region where solutions are quite reliable, and it doesn't have a brain lesion. The lesion has disappeared, and this solution is still fine. So clearly, your data doesn't feel that strongly about the presence of a brain tumor in this image, because I just need to move a bit in the parameter space. I'm still in a region of high probability, and suddenly the tumor has disappeared. So maybe you should not rely on this measurement. I don't know, do more measurements or reduce the noise level, or just be aware of it. However, if you stop at two solutions that are as close to each other within the sets, but they don't touch, then you can say many things. You can say, well, there is no solution that belongs to both sets, so the probability of H0 has to be smaller than alpha. And you can also say, by comparing the two images, this, I don't know, this brain tumor or this structure in my astronomical image has to have this amount of energy, because that difference is a bit the signature of your star or whatever. And you have tried to make the energy of that star as little as possible to remove it. And you have failed to go any further than a certain amount. So this tells you a bit, maybe this star, well, this star is there, and maybe it doesn't have as much energy as you think, but it has at least this amount of energy, because that's the minimum signal that I can get away with at level 1%. So we revisit the example from yesterday, MRI image, very undersampled, so I don't have enough Fourier measurements to do the inverse Fourier transform. I use a model that promotes sparsity on a specialized wavelet dictionary. I reconstruct this image. There is a lesion here. This lesion is something I'm worried about. So what I'll do is I'll construct a set of solutions, and the way in which we construct it is we basically say all solutions such that this region of the image results from interpolating the other parts of the image. So I'm looking at any image where there's no new information here. The information that arises here arises just from doing an in-painting of the rest of the image. Okay, so if I did that, I would airbrush my solution, my lesion, and it would disappear. So I define a set. I have to do linear interpolations because otherwise my set is not convex. We are now working on a refinement that does nonlinear interpolations, but basically you say anything that you find here has to be a linear interpolation with some, good filters of the rest of the image. That defines a set of possible images. And you also add energy bounds. What is interpolated here, I know, should not be negative, should not be, if this is on a scale from 0 to 1, it shouldn't be larger than 1. You add basic things like that. And you get a set of solutions S. And here I find 2 points, one in C 1% and one in CS, that are as close to each other. And it turns out they coincide. So in this setting, this is a counterexample. This is a good solution that doesn't have the lesion. So I can conclude that I will not be able to reject H0. I cannot reject that there is not a lesion here. Right, so maybe there is one, maybe there isn't. In any case, I'm too undersampled in this MRI image to do that conclusion, at least based on this model. Another image with another lesion. So let's say I look at this structure here. It appears here. I'm sorry, the contrast on the computers is always much better than on the screen. But here there is a small gray area that is a bit lighter than around its neighborhood, and I want to check if it's really there or not. So again, I will try to make it disappear. So I have a set S that will airbrush that area and in-paint it with information from other parts of the image, whatever that other parts of the image might be. I don't ask for specific values. I just say that region cannot have new information. It has to be interpolated from the rest of the image. And I look at all possible other images of cats, dogs, whatever you want, that interpolate that from the other area. And what I see is that C alpha does not authorize that. C alpha has to have information here. The two images are different in this region. They don't touch each other. So that means that the model is allowing the solution to move here up to a certain level, or here in my drawing, but it can't actually get into S at level 1%. There's a difference between the two. So I can conclude that the probability that there is no lesion, or that this structure does not exist, sorry, is smaller than 1%. So I'm happy to say that I think there is something here. And yeah, and I'll sort of like claim that within the limitations of my model and the approximations that I'm making about the real world, it looks like the data supports something here that is not just an interpolation of other things. And if I do that for the radio astronomy experiment, I can look at different structures, and what we did here is take different numbers of measurements. So here I'm showing all the measurements that we have. So that's like 1,000 or 2,000 measurements, and then I'm subsampling that. I'm assuming that I've only taken a certain number of measurements. So these measurements arise from measuring for a certain time period, and I'm assuming that I stopped the time period a bit earlier. So I measured for just 100, 200, 300 measurements or sampling periods. And I see how these three structures behave. So when what I'm plotting here, rho, is the ratio of the energy as I see it here if I were to airbrush these structures and see how much energy there is in these regions as opposed to just background information. And I'm comparing this, so I have it here, against the energy that I observed after looking for 2 points that are as close to each other in the sets. And what I see is that when I have 1,000 measurements like here, then I'm quite confident about the main structure here. I'm okay about that one. And this one, the red one, is more difficult to justify. And as I take my sampling period, as I make my number of samples go smaller and smaller and smaller, this ratio actually goes down quite severely. So if I was working with just 400 samples, because let's say I wanted to move on to a different object in the sky and I don't want to use my radio telescope for so long and I just observe 400 samples, then clearly that would be enough to trust this region. Sorry, this is the strongest structure, but this one would be below 1% and this one would be completely out of the question. If you want to be confident about this one, then you need to continue observing a bit more, and you observe a bit more, observe a bit more, and eventually you get to a value that is a bit better. In any case, we're not very sure about this one. This one is quite okay. This one is definitely there. So you can acquire measurements, and if at some point you decide that you're interested in a specific structure, but you're not sure about whether that structure is above your noise level in a certain way, then you continue acquiring measurements until you can make a more definite conclusion about whether it's there or not.
In this application, when you increase the number of measurements, you improve the SNR or you improve the conditioning of the observation operator?
I'm not really sure. I always struggle to understand how they define SNR in this problem. So they definitely don't improve the SNR in the sense of the additive noise that appears on the number of measurements. And you definitely do improve the conditioning number because the more measurements you make, I mean, your operator is rank deficient. And by increasing the number of measurements, you are increasing the rank. So you are improving the conditioning number of the whole posterior. Conditioning number is not properly defined because the posterior is strictly convex and not strongly convex in the directions that you don't observe. But you're definitely making the problem better posed by improving the number of measurements. You are not necessarily concentrating the likelihood. However, they use this other definition of SNR that depends on the number of measurements and not just the noise level, and that SNR you do improve.
And so coming back to this conditioning issue or quantification of the conditioning of the well closeness.
Yes.
Where is in the definition of the C alpha tilde is the conditioning appearing?
Well, it appears implicitly. So because I'm comparing the value of phi against a certain gamma, if I improve my conditioning, then my phi will become more like this. So as soon as I move a little bit, I will get very far from the optimum value. So I'll cross C alpha very quickly. Whereas if my conditioning was worse and my function phi is very flat, then maybe it will authorize, it will definitely authorize much larger explorations without increasing too much. And that will lead to very large regions. But it doesn't appear explicitly as a parameter. Do you have any other questions about this part on uncertainty quantification? Yeah?
Can you come back to slide 19? It's regarding the construction of S. So you say you're authorized to do inpainting or linear interpolation of any of the pixels from, let's say, your region of interest. But I don't know, is there a possibility to create a fake lesion using any sharp border in the image?
So what we do is we ask that it has to be interpolated, and then we put constraints on the energy of that region. So that way we rule out solutions that have unreasonably large amount of energy. So we force pretty much this interpolation to generate things that are within a neighborhood of background, what we consider to be a background level. However, the design of the filters is a bit of a craft yet. I think it would be good to have someone work on it for a couple of years, maybe to have a PhD student, think carefully about how to automate, not make it automatic in the sense that a computer will do it on itself, but how to have a clear set of guidelines that this is how you should design your region. So far, we've been working with linear filters, and what we know is that it would be much better to work with a non-linear inpainting procedure. But then the solution of the feasibility problem becomes tricky. Yeah?
So when you do this test, you have this notion of power of the test. So basically, so my intuition is that if you overestimate the C tilde, then you're going to have bad power in the sense that you're going to miss a lot of true. So how much as having this upper sets is it giving you like a lack of power, or can you quantify this?
Yeah. So we can't quantify it theoretically. We have not done that yet. There's a number of tricky things. So power, in its most popular definition, is a frequentist property. So we have not yet looked at the frequentist coverage properties of these Bayesian tests. But we have done experiments where we compute this with the approximation and with the exact region. So we do the experiment by MCMC. And we are getting consistent results, except for some small structures that are tricky. So there are cases where you're failing to reject because of the approximation. So what we recommend is that if you can reject with the approximation, then you're fine. If you see that the solution is really far, you're fine. If you're a bit near, then maybe switch to MCMC for that specific problem and do MCMC. We are working a lot on accelerating the MCMC algorithms. So hopefully at some point you will not need to use this. But at the same time, they are working a lot on increasing their image sizes. So it will always, will always lag a bit behind. So I don't know, if you wanted to do this on 3D MRI, then clearly MCMC would be, even the new version that is going to come out soon, that is faster, is going to struggle. Okay, so if it's good with you, I'll now move on to something else. Something is more theoretical. Then, depending on how much time we have, I'll either cover hierarchical map estimation before or after the break. And there's another presentation for after the break on advanced Bayesian models. But that one, I can either do half of it, or I can go a bit faster, or we'll decide based on the time that we have. I definitely don't intend to cover all of the material. It's better that we do what we do, and we do it well. So stop me when you have questions. This is going to be a bit esoteric, so you should have questions at some point. So Okay, so how do Bayesian estimators arise? We described this yesterday briefly, but today it's going to be one of the three key topics that I'll describe. So Bayesian estimators don't arise from me just saying this is my estimator. It works the other way around. I have to say this is my loss function. This is how I want to measure error. So if the truth was that, I don't know, my weight is 85 kilos and you measured 87 kilos, then the error is measured in this way, 87 minus 85. Okay, absolute value maybe. If you're working with mean square error, then it's 87 minus 85 squared. But for images, it's not very clear what measure of error you should be using. So we said if I take an image and I just add a constant value to all pixels, that will lead to a huge mean square error. But for visualization purposes, that image is just fine. It's almost, I mean, the eye will not pick up on this difference. And yeah, why should I penalize so much that image? And, and more generally, it's not very clear what loss function you should use. So what I said yesterday, one of my elephants, was that we should start thinking more carefully about how we're going to define this loss function. And the machine learning community now is working a lot on loss functions because that's something that neural networks are very sensitive to. So maybe this is an opportunity for the imaging community to piggyback on that and also start reflecting on our loss functions. But in any case, so what we know is that we want our loss functions to verify three general desiderata. The first one, we want it to be non-negative. We want it to be 0 only if the 2 points are identical. And we want it to be strictly convex with respect to its first argument, because otherwise we don't have estimator uniqueness. There are good loss functions that are not convex with respect to the first argument, but if we don't have that, then we expose ourselves to estimator non-uniqueness, and then we would have to do some extra work to analyze what happens in that case, and potentially decide what estimator we're going to report if there's more than one solution. So we try to steer away from this. And if my loss function was just the quadratic error loss, then we said that the Bayesian estimator in that case is the minimum mean square error, which is just the mean of my posterior distribution. So if my model is something like this, then I don't know, the mean falls here. This would be my Bayesian estimator. And I could take the median, I could take the maximum. And usually in imaging, we are taking the maximum. But we also said there's not a good theoretical reason for taking the maximum. There's this argument that this is the result of using the 0-1 loss function. This makes sense with discrete random variables. With continuous random variables, it doesn't. And then we said, well, but what we're doing is we're taking a sort of like a ball of size epsilon around the point, and if you're within the ball, it's 0. If you're outside, it's 1, and we're letting the radius of the ball shrink to 0. And this is the argument that is advanced in most textbooks. And someone recently realized that these two limits don't commute. So you're not allowed to do that. If you let the radius go to 0, your estimator does not converge to the estimator that you have. So the way I read this is that this is a problem that we have completely neglected. We felt like, well, we're computing the maximum. We don't know why it's good, but we can live with that. And there's this excuse that I can do a 0-1 loss function, but we've never really bothered to check if this was sensible or not. So what I wanted to do was to see if the fact that we had a convex geometry in our model, because everything is log-concave and phi is convex, if this could somehow inform the loss function that we should use. So could I let the model in some way define the loss function? Because I really like the model. It has some defects, but usually they do a good job. So can I somehow infer a sensible way of measuring distances or differences between solutions by using the convex geometry of the model? So does it define an interesting loss? So to do that, you can use differential geometry. And by using differential geometry, we can relate the convexity of your model, so the convexity of phi, to the convexity, so to the geometry of the parameter space. So to explain this, I need to introduce a few ideas related to Riemannian geometry. I'll try to keep it at a very intuitive level without going into any complicated definitions. But let's just say that a Riemannian manifold is something that behaves locally like an Euclidean space, but there are a few things that are position dependent. So you can have an Euclidean space where you measure the norm in a certain way. So for instance, U transpose X is the standard way of measuring the inner product in a canonical Euclidean space. But you could put any matrix here, let's say Q, and define other inner products. So if you define other inner products, you get other ways of measuring the norm of X. And the key thing of a Riemannian manifold is that you not only have your Euclidean space, you also have a function that for each point of your parameter space gives you a matrix Q to do inner products. So here I call that matrix Q G of X, and it's what we call the metric of the parameter space. At each point, it outputs a positive definite matrix that allows you to multiply 2 points in that space and see what's their inner product, and also defines a norm. And crucially, this metric may be position dependent. So when you're in a certain part of the space, you have a certain norm, and if you move to another part of the space, you have a different norm. But those norms are not allowed to change in a crazy way. You want them to vary smoothly. So this function g is differentiable, and if I look at its derivatives, I get what we call the affine connections. And this is just an object that tells you how your inner product or your norm changes if you're standing at point x and you move to point x plus delta x. So at each point x, you are locally Euclidean. You can think that you have what we call an Euclidean tangent space. And around that point, things behave well, quite in an Euclidean way. And then when you move to another part of the space, again, locally, you're Euclidean. And it turns out that when you have an Euclidean manifold, you can define a class of functions that are quite relevant in geometry called divergence functions. So you've heard Clarice, for instance, talk about Bragman divergences. And there's a large range of divergences that we can use, and they are formally defined as any function that takes 2 arguments, and it's not negative. It's only 0 if the 2 arguments are equal, and then it is strongly convex with respect to the first argument and continuously differentiable with respect to both arguments. So these divergence functions, they look a lot like what Bayesian statisticians call their desiderata for a loss function to define an estimator. So maybe divergences are good candidates to define Bayesian estimators. It looks like the 2 classes of functions are very similar, except for the fact that here I ask for strong convexity and I also want differentiability. So given that I have a Riemannian manifold and I have divergences, the next question, and I'm suggesting that I would like to use a divergence to define a Bayesian estimator. The next question is, which divergence should you use? And now I want to explicitly state that what I'm thinking of doing is saying that although my images take values in an Euclidean space, so the values are Euclidean vectors, the geometry of the space is not Euclidean. I want to let the geometry of my parameter space be non-Euclidean, be Riemannian. And once I do that, I start having lots of options of how I'm going to measure distances depending on what Euclidean geometry I induce on my parameter space. And once I induce a specific Euclidean geometry, then I have a very specific divergence that I want to use, which is called the canonical divergence of the parameter space. So although you can define any divergence you want, there is one that is a bit special. So for each Riemannian manifold, once you specify G, you get one specific divergence called the canonical divergence that verifies this integral. And it is canonical because if I give you G, D is automatically defined. But if I don't give you G, I just give you D, then G is automatically defined. So D has all the geometry information of the parameter space. If you know D, then you have fully specified your Riemannian manifold, as if you had defined G. There's a one-to-one equivalence between the two, so that's why we call it the canonical one. And so D fully specifies the geometry. D is locally like using the Euclidean norm. So if you're in a point and you stay in the neighborhood and things behave quite Euclideanly, then using D instead of the Euclidean norm will not make a difference, in the sense that you'll have an error that is very small. And for Euclidean spaces, then D effectively becomes the Euclidean square distance. So if you will have something like a Malanovis distance or the Euclidean square distance if G is identity. So it's a generalization of the Euclidean square distance. So it's a generalization of the mean square error to settings where you're not Euclidean. So then we have this interesting theorem. Suppose that sorry. Suppose that your model is log-concave. And now I need to ask for a bit of differentiability. So suppose that it's log-concave. So phi is strongly convex, and I'll assume that it's 3 times continuously differentiable. Then we can talk about what happens when I relax these conditions. So what happens in that case is that the canonical divergence has a specific analytical expression. I can write it down. This integral has a solution that I can write down explicitly, and it's the Bragman divergence associated with phi. And this is the same Bragman divergence that Clarisse was talking about. At some point, I think you talked about the Bragman divergence in the case where phi is not differentiable, so that it has a subdifferential. That's sort of like a next step. It's not a divergence in the strict sense that I described earlier. Here, the Bragman divergence has this expression. So I need differentiability. So what is this Bragman divergence measuring? Well, it's measuring the convexity gap of my function. It's measuring what happens when so I know that if my function is convex, then if I go here and I estimate this value by doing a linear extrapolation, then this quantity has to be positive, because that's what convexity means. It means the function stays always above the tangents. This value here is the Bragman divergence. And this, it turns out, this measures the geometry of the parameter space in this way. It measures distances by following the affine geodesics. So you have some geodesics that are ways of measuring distances in the space. And if you move between mu and x, following that geodesic, and for each delta step that you take, you look at the norm of that delta step in the Euclidean space where you currently are, and you accumulate all those delta norms, then you find the length of your affine geodesic, and this is what you're doing here. You're going from u to x by integrating those affine geodesics in a specific way, and that's exactly what your Bragman divergence measures. Okay, so the canonical divergence is the Bragman divergence in this case. And then what happens if you define the Bayesian estimator for the canonical divergence? What's the best estimator to minimize this? Well, it turns out it's the map estimator. So if you say, well, my model is log-concave, phi is convex, and I will let phi induce the geometry of the parameter space. I would let the Hessian of phi define a Riemannian matrix and tell me how to measure distances. And now I want this Bayesian estimator that is optimal with respect to this way of measuring the error. Well, it turns out what you need to compute is the map estimator, the minimum of the loss function. So the way I read this result is that for all these problems where we have convexity and where we have observed that the map estimator is really something good to compute and where it performs really well, in many cases much better than the mean, what we have been doing without being aware of the fact that we're doing it is computing the canonical estimator for that model. At least it's a much better excuse to using the model than the 0-1 loss function. And this highlights that this definition of the map estimator as the maximum is just algorithmic. When you're saying the map estimator is this, or the minimizer of phi, you're talking about the algorithm or your algorithmic approach to computing it. But that's not how your estimator is really defined. Bayesian estimators are defined as optimizers of expected losses. So that's a more appropriate definition. And then there's a nice duality property. So let's say that I flip my divergence. Instead of putting u and x, I put them the other way around. Divergences are not symmetric. That only works for distances. So I'll get a different estimator. And it turns out that the other estimator is the posterior mean. So the mean and the map are dual to each other in this sense. There are two canonical estimators for any model, provided that I have convexity. So yeah, so this is an interesting result that highlights lots of relationships between map estimation and decision theory. So it turns out that the map estimator is a proper Bayesian estimator in the sense of decision theory. It also turns out that from a theoretical point of view, it is arguably as solid as doing mean square error estimation. It's not too difficult to defend why it works better than mean square error estimation in some problems. I'll talk about this in a minute. It comes from letting the geometry of the model induce a Riemannian geometry on the parameter space and accepting that when I compare two images, I'm not going to do it just by their Euclidean difference, but by something that is a bit more involved. And these results carry partially to situations where I don't have differentiability, or I have constraints on the parameter space, but they carry partially. So I invite you to check the paper to see what survives and what doesn't. A few things carry. So the fact that the map estimator is the minimizer of the Bragman divergence survives if you don't have differentiability. But then it doesn't make sense to talk about a Riemannian manifold, because if you don't have differentiability, then you're in very tricky lands when it comes to Riemannian manifolds that have degenerate metrics and yeah, so forth. Okay. Now, what can you do with that result other than justify using the map estimator to Bayesians? Well, one of the things you can do is look at how your estimation error behaves when you measure estimation error in this way, since your estimator is supposed to come from that way of measuring error. So what we know is that for the dual error, so I'm measuring instead of x and instead of u and x, I'm flipping them around. So I'm looking at geodesics when I integrate them in the other sense. We can show that the dual error of the minimum mean square estimator, so the mean square estimator is the optimal for the dual error. So it has an expected error that is lower than the map error. But these two, they are lower than 1 for any model, as long as you have convexity and things are once differentiable. So if I take my error and I divide by the number of pixels, which I need to do because obviously if my image is larger, then the error will increase. But the error per pixel cannot blow up if you use these estimators. You can let the dimension be as large as you want, but as long as you have convexity, then the map estimator and the minimum mean square estimator will give you an expected error that per pixel cannot blow up. It has to increase at most linearly with the estimation error when you measure errors in this correct way. And when I tried to publish this, one of the main worries of the reviewers was that this function depends on the model, and the model depends on the data, so I could potentially have a different loss function for each data set. This doesn't always happen. There's many cases where the dependence on the data cancels out and it disappears from the model. This will happen whenever you have a Gaussian likelihood. But it was still a concern. So there's this additional result that says if you now measure the error using just the prior, so this is very similar to what Clarice was doing. She was looking at penalizing with something like an L1 norm and then looking at the error with the Bragman divergence associated with that, I think. So in that case, we have the same guarantees. The expected error with respect to this Bragman divergence, which people in the variational community use frequently, is also bounded by 1 for both estimators. So this gives us confidence that in high dimensions the estimators will work well. This is not new. We had empirically already discovered that they work well and we use them all the time. Now there's a bit of theory to support that. Okay, so in the interest of time, no, I'll explain this in detail, then we do the break and then we do something else. So let's revisit a bit a model where I have something that behaves like an L1 norm and I'm promoting sparsity. I like this example because it's a controversial topic. A lot of people feel, as I said yesterday, very strongly about whether what you're doing is properly Bayesian or not. In some communities where Bayesian statisticians have the higher ground, they say that people doing penalized L1 are just using a Laplace prior. And then in other communities, the people that have a more applied math background have the higher ground, and they claim that Bayesians are cheating by saying they're doing Bayesian inference, that they're just doing penalized least squares regression. So my 2 cents to that discussion are the following. So if you use this prior, so this is a prior that is very similar to putting an L1 norm, but it has a parameter gamma that will make things just a bit smoother so that my theory applies. So let's say my prior was like this, and instead of having an L1 point that is discontinuous, here I have a bit of a quadratic change. Then I can get this by using that, that function called the smoothed Laplace, or the Carbonnier, or the pseudo-Huber. This has been proposed by like 10 different people with 10 different names. So let's say I use that prior on the wavelet coefficients of an image. So I have an image that I observe, and I'm going to put a prior on the wavelet coefficients. I'm going to assume that I have a orthogonal wavelet transform, and my prior on each coefficient is this. And the likelihood is going to be a quadratic likelihood that I can write down with respect to wavelet coefficients by adding the inverse wavelet transform there. And then I have a posterior distribution that is quite trivial. There is a quadratic term, and then there is this pseudo L1 term there. And I use this model for my illustration because it is infinitely differentiable and strongly log-concave. So my theory will survive. Now to analyze the geometry of the model, assume that A is the identity, so I'm in a denoising setting, because otherwise getting really fine analytical results is difficult. So I'll assume I'm in that setting. And what I'll obtain is that, of course, the Bragman divergence in that case is separable. So the divergence on the whole vector is the sum of the divergence for each pixel. And the non-quadratic term that I have induces, okay, so this is the key thing. The Bragman divergence is a quadratic term plus this term here. So when I'm computing the map estimator and I'm trying to minimize this loss, I have a quadratic term. And if I was just computing the mean square error estimator, I would also have a quadratic term. And then this extra term here, the non-quadratic term, is what makes the difference between computing the map estimator and the minimum mean square error estimator. This is why the two estimators do not coincide. And if you've ever done a bit of soft thresholding or played with wavelet denoising, you'll know that the map estimator in that case works really well. Thresholding your wavelet coefficients, which is what this would do, works really well, whereas computing the posterior mean would not work very well. I mean, you've probably not done that. I've done it, and it doesn't work very well. And that's one of the arguments why people say this is not a good Bayesian model, because look, if instead of the map estimator I use this other estimator, then I get bad results. Well, to develop an intuition about what is going on and why this is non-quadratic and why it is important to have it, we're going to analyze how this behaves. So we're going to look at what happens when Z is really large and really small and things like that. So when Zi is really large, then the non-quadratic term vanishes, and then I have this. So what that means is that when my posterior model wants pixel values or coefficient values wavelet coefficient values that are fairly large, then those large values, whether I go for the map estimator or the minimum square estimator, will be estimated similarly. The minimum square estimator is optimal for any quadratic loss function. This is a quadratic loss function. So when I integrate out this function over possible wavelet coefficients, if my model is putting all the weight on large wavelet coefficients, then I'll be essentially integrating out this function. So the optimal thing to do would be to choose u equal to the average of my posterior probability for the coefficients zi. So will the model promote sparsity? So here I call that promoting shrinkage. Will it promote sparsity or not? Well, not for large coefficients. You'll just estimate the posterior mean. It will promote a bit of shrinkage because my prior is going to behave a bit like this. So it's going to be centered around 0. And even though my, my posterior distribution depends on a Gaussian likelihood, because I'm multiplying maybe two things, one that looks like this, centered around, I don't know, 1 or 10, whatever, because of my observation, the product of the two will tend to go towards 0 because of the prior. So this is the normal Bayesian way in which the prior acts on the likelihood. So will it promote sparsity? Yes, a bit through the prior, but not through the estimator. So in this case, you should get the same if you're using the map or the mean square estimator, because all the shrinkage comes from the prior. What happens when zi is small? And it's small, so it's close to 0. Well, then we observe that in addition to the effect of the prior pushing the likelihood to 0, then the loss function that you're using to compute the estimator brings additional shrinkage. So when zi is small, then when you're selecting the u, you have something that looks like this. You want a u that is really close to 0. Why? Because you have this term here, and z is close to 0, so you're going for something that is quadratic, so it would be the average value of z. But you're adding a L1 penalty, and you're doing the minimum of this. So you'll get something that looks like the posterior expectation of that wavelet coefficient shrunk to 0 by your L1 norm. And this is in the case where u is small, sorry, when u is large, and when u is small, you also have extra shrinkage in the form of amplifying the convexity constant of the model. So leaving the mathematical details aside, the message is that what happens is that when your model likes values of z that are fairly large, then it will just go for the average value of the posterior when you compute the map estimator. But when you go for small values of z, when your model promotes small values of z, when you compute your estimator and decide how to summarize all those values, which one to choose as your summary, it turns out that your loss function amplifies shrinkage. It will promote solutions that are summarizing this in a way that promotes really small values of z that are equal to 0, in fact, in this setting, and very close to 0 in this setting. So when you are in that situation, you have used a certain model to describe your signal. You have said that your prior looks like this. Your true signal was sparser than this. So maybe your true signal had a lot more concentration around 0 than what your model suggests. So your model is not going to shrink as much as you would have liked. Your posterior is shrinking, but not as much as you would have liked, because you went for a model that is a bit misspecified. When you use the map estimator, you are boosting the shrinkage by your choice of the estimator. And because you're boosting your shrinkage, you partially compensate for the fact that your model was not very well specified. And you get a solution that looks very sparse. And when you go for another estimator like the mean square error, then you're relying on the shrinkage of the model. If the model was shrinking enough in the first place, then it's fine. If it wasn't, then it's not. So for instance, in this image, I show what happens if you compute the two estimators, and clearly the map estimator is much better than the minimum square estimator for denoising this Flintstone image with a wavelet. And if I look at the function that maps an observation to its value, so a wavelet coefficient here to a wavelet coefficient here, I see that there's a lot of shrinkage. So a value here will be shrink to almost 0, very non-linearly for the map, and almost nothing for the posterior mean. So this is an example that I designed on purpose to be in a situation where the model is not shrinking nearly enough, and I really rely on the choice of the estimator to promote shrinkage. But there's a warning. This is not always true. In a very similar model that is also quadratic likelihood and L1 norm on wave-length coefficients in radio astronomy, the map estimator and the minimum square error estimator are behaving exactly the same. Why? Because these radio signals are not as sparse as we would like to make you believe. They are more like generalized Gaussians, so they are sparse but not that sparse. And then the approximation of using a Laplace prior is absolutely fine, and you're getting all the shrinkage you need just by doing that. So in this sense, the model here is really good. In the other sense, the model was a bit too misspecified. Okay, so let's stop here. And we're a bit late, but we can take a few questions. Maybe we'll have 5 minutes less for coffee. I don't know. I think they would like you to use the mic because they're recording the lecture, and otherwise we won't hear your question.
So coming back to what you showed with the thresholding functions that you had just right here. So I did not really understand what you were displaying on this curve. Can you re-explain why you see this types of?
So so this is taking noisy wavelet coefficients as input and outputting denoised wavelet coefficients. So the noisy wavelet coefficients, they go into the model, and if you're computing the map estimator, they are mapped to a value that is very close to their original value, not changing a lot. That's why the noisy image and the denoised image have almost the same SNR. There is a bit of shrinkage, but it's not visible in this plot. Whereas when you compute the map and you put a wavelet coefficient that is a bit large, then you don't shrink it at all because of the results that we saw. It's behaving like the minimum mean square estimator. Whereas when you put a small wavelet coefficient and it lands, so let's say 0,1 lands here, the map estimator will reduce it to very close to 0. So it's doing a lot of thresholding.
So the fact that you see something that doesn't look perfectly like a soft thresholding is due to the gamma?
Exactly. And by the way, if you use gamma equal to 0 to really promote the L1 norm, your results would significantly deteriorate. Instead of 19.8 dB, you would go down to 18.8 dB, which is better than this, but halfway there. So for these models, if you look at the wavelet coefficients of a clean image, the tails are sort of like heavy, but you don't have a peak of values around 0. The original wavelet coefficients, you don't have that many values that are actually close to 0. It behaves a bit like a Gaussian function in the center, and it has tails that are well described by the Laplace. But they are quite close to a generalized Gaussian function, and the generalized Gaussian function is not, in the center it's not that discontinuous. So it's interesting that in that particular sense we have regressed a bit. In the 90s, people were proposing lots of loss functions that were quadratic around 0 and had tails that behaved a bit like exponential tails. And there's, I don't know, at least 15 good functions you could use, Huber-type functions. And then in the last 10 years or so, we have focused really on L1-type functions that around 0 are good at promoting exact 0 values, so like to get very sparse solutions, but the original signals are not that really sparse. So, yeah.
Any other question? Nobody? Okay, so...
Aren't you going to ask me how it compares to MCMC? No, I'm kidding. We can stop
How
for
does
coffee.
it compare to MCMC? Marcelo,
It's
please tell
faster.
me.
It's faster, it's less accurate. We should be doing MCMC instead, but...
We see that in half an hour.
Okay.
So I have something to tell you about the attendance certificate. So if you need, yes, if you need an attendance certificate, we can give them to you at the coffee break. There are two persons who they didn't fill the form. So if you didn't fill this form, come to us at the coffee break. Okay? Thank you. It's a form about the Friday lunch.
Thank you. Good. Okay, so microphone on. Yeah, okay. So let's finish this first talk, and then we'll move to a second one, and we'll decide what we want to see about that one. So, okay, yesterday I also talked about setting regularization parameters. This is something that I encountered very often during my PhD, and that was a big source of frustration for me. So at the end of my PhD, I decided that my contribution to mankind would be to find ways to set regularization parameters. And yeah, so let's assume that I have priors that are of this form. So my prior is indexed by some parameter theta, and yeah, it acts by weighting how much I promote properties that are in agreement with H and how much I authorize things that are not in agreement with H. And, oh sorry, typo, this should be C of theta, like here. So when theta is fixed, if my posterior is log-concave, this object here, which is the function I had described as phi, is convex, and I can find the minimizer by convex optimization in a very efficient manner. But when theta is not known, then things become complicated, and even optimization would not be straightforward at all, because now theta is not known, and if I want to optimize with respect to theta and x, then I have a function here, c of theta. The normalizing constant of my prior, which we talked about yesterday, is a big integral. We'll see it again. And this is not a function I know. So I can't minimize this. I can't do much even if I'm not trying to minimize it, because I don't know it. So even MCMC becomes a big problem. And yesterday we talked about one MCMC strategy to estimate theta by putting an MCMC kernel inside an optimization algorithm. Today we are going to talk about something else that does not involve MCMC sampling at all, which is the theme of this lecture. And then there's also the normalizing constant of the posterior log p of y, but this term doesn't depend on theta or x, so we'll ignore it for the rest of the time. So here we're going to focus again on this infamous problem of not specifying theta. Rather than trying to find a value of theta, I'm going to try to not have to find a value for theta. And we're going to do that by postulating a Bayesian model that works on x and theta simultaneously. So the philosophy is the following. You don't know x, so you put a prior on x, and you have a posterior distribution for x given y. Well, we don't know theta, so let's put a prior on theta and incorporate it in the model and say my model represents both unknowns, x and theta. X is a large vector, theta is a scalar. Nevertheless, you can put them together and say what is my model for x and theta given y. So we'll put some prior on theta and get a model for x and theta. And now c of theta is, again, this integral, which is untractable. I don't know how to compute this integral, so I have a term here, c of theta, that is problematic. So following this approach is problematic because there is c of theta. If we had theta, then we could either estimate x and theta jointly, or even more beautifully, we could marginalize theta, so integrate out theta from the model, and get a function that depends only on x given y. And this is what we described yesterday when I said I will work with all models at the same time. I marginalize out theta, I integrate it out, then you have a function that works with all models simultaneously, but where the data is deciding what models to use more than others. So why don't I use MCMC sampling to find C of theta? Okay, let's run an MCMC chain, pre-compute C theta, and then estimate value. So I did that. Now that I had my brand new MCMC algorithms, the proximal MCMC that we saw yesterday, I'll compute C theta and store it, and maybe I'll do that for lots of values and put it in a paper so that everyone can use it. But when I did that, I found something strange. So the strategy I used was to use this identity, log of the derivative of log C of theta is equal to this expectation. So this was my strategy. MCMC can estimate this expectation. From this, I can get this function, and I can numerically integrate it to get C of theta. When I do that, I get a straight line. And this plot, this should be theta. It's just, yeah, I used to call this lambda. So theta and the expectation I find are a straight line. So the logarithm of this behaves like a straight line. The derivative is a straight line. And it happens for Laplace, it happens for total variation, it happens for the nuclear norm, it happens for Laplace on wavelet coefficients. So there's something interesting going on. I knew it would happen for Laplace because in this case the function is available analytically, but I wouldn't expect this to be the case in all the other models. So it felt like maybe I don't need to do MCMC sampling to find these things. Maybe there is, an analytic solution. So I started looking for it, and I found this. So if your penalty function is k homogeneous, that means if I have a scalar multiplying x, a positive scalar multiplying x, and I take it out, then I get the same value, but it's the scalar power k. And this for any x and any scalar. All the norms that we use to penalize things are homogeneous with order 1. Even if you do a norm on a dictionary, so you have some linear operator, an L1 on wavelets or whatever, it is homogeneous with order 1. The L2 norm squared is homogeneous with order 2. So all the things we are using are homogeneous. And in that case, it turns out that you can analytically find the normalizing constant by using a change of variables and a few other basic things. And you can show that the normalizing constant will be theta to the power minus d over k, where d is the dimension, times a constant d, that is c of 1. And now this term is still untractable. It involves an integral I can't solve, but it's not a function of theta. So I will ignore it conveniently. So here I have my c of theta. And it works for all norms, L1, L2, L1 and L2, compositions, analysis priors, things like that. So maybe I don't need to do MCMC sampling at all. What I can do is, sorry, I forgot to replace theta again here. So, well, lambda is the regularization parameter. So I have my joint model for x and lambda or x and theta, and I marginalize out the realization parameter. And when I do that for these models using the expression of c of theta that I just gave you, and this specific prior, a gamma prior, which is something that is analytically nice and that will have no impact whatsoever in the solutions, what I get is this new cost function. So if I wanted to compute the map estimator for this density, the one that doesn't depend on theta, I would have to minimize this new cost function, which has still the data fidelity term from the likelihood, but now the prior that used to be h theta is now log of h, and there are some other parameters, but theta has disappeared. Dimensionality over k is known, but I have alpha and beta that are parameters from the hyper prior, the prior on theta, and I need to set those. However, alpha is being compared to d over k, and dimensionality is really large, and k is usually 1. So, you can choose whatever you want for alpha, and it will not make a difference. Usually, I go with alpha 1, and that's it. It doesn't impact the solutions. And then h of x is usually also quite large, because x is measuring, I don't know, let's say the L1 norm, and x is very large, so you're doing the sum of the absolute value of all the pixels. By the time you have 1,000 pixels, you usually get a large value. So beta is again not important. So I usually just use 1 and 1. In some cases, you do observe a bit of sensitivity, and then you have to be careful, but in general, 1 and 1 are absolutely fine. Otherwise, what you have to use is values of alpha and beta that promote values of the regularization parameter that you have already empirically observed are sensible. So if in your experiments you have found that regularization parameters between 10 to the minus 3 and 100 are good values, then you can choose alpha and beta such that this gamma distribution takes values roughly in that support. Okay? Once you do that, you can compute your map estimator by solving this optimization problem, which is difficult because this is not convex, but luckily we can transform into a sequence of convex optimization problems by doing something we call majorization minimization, which I will not explain in detail, but basically what you do is you take your function, and maybe it's not convex, so it could look like this, and then what you do is at iteration t, you construct a convex approximation, and you minimize it, and that takes you here, and then you do that again, and you minimize it, and you do that until you get to a local minimizer. And it is not in the OSIPCO paper, but in a journal version that will appear shortly, we show that this converges. And numerically, you observe it always converges, and there's never more than one minimizer in the experiments I did, and there might be more than one minimizer in one experiment that Anna did, but yeah, that would still not be the end of the world. So local minimizer, you could get stuck, but usually it doesn't happen. So yeah, and this is also what we know as an expectation maximization algorithm, which is an algorithm that people use quite a lot in stats. So how does it work on an example? Well, standard compressive sensing setup, X is observed through phi. Phi is a compressive sensing matrix with random components that come from discrete cosine transform or something like that. It's a very standard compressive sensing setup. And I add some noise, and then I want to recover X, and I will use this analysis prior that promotes sparsity on a wavelet frame. And this is homogeneous, so I can apply my method. And I do that, and I recover a good value of theta in both cases, and good reconstructions with these two test images. And yeah, so it seems to be working fine in these two cases. The question is whether we could have got really bad results if we had chosen theta incorrectly, and how this compares with other strategies. So we compare that with other things. So we compared it with an oracle that knows the best possible value for theta. And we observed that the oracle gets a PSNR of 33.5, and we're at 33.4. So we're not far from the oracle. And yeah, and if we compare with sugar, which is this other method that is really state of the art that was proposed by Gabriel Pereyra and Jalal Fadili and a co-author, we observed that in this specific case, their method again works really poorly. So as I said yesterday, sometimes their method is better than ours. So this is not a problem that has been definitely solved, and I don't claim that you should always use our method. I am just claiming that unlike what you might conclude by looking at the results of their paper, there are cases where the method does not work well, and there's scope for improving things. And yeah, you would not deduce that just from this plot, because I'm doing the same thing. I'm claiming that my method works really well and theirs is rubbish. So I want to stress that all methods fail. And then in the other image, you have more or less the same conclusions. And if you look at what happens for other values of theta, well, you see that if you're not in this sweet spot, then you get a very bad reconstruction. So it's not surprise, compressive sensing is a very ill-posed problem. So unless you choose well your regularization, you get rubbish reconstruction results. And the algorithm is managing to find a theta that falls quite close to the oracle value for theta. And if you look at how long it takes for the algorithm to converge by doing this majorization minimization, you see that it takes only a few number of iterations. So in 7 iterations, theta is stabilized at the value that we will use. Sugar also converges quite quickly. In something like 10 iterations, it has stabilized. So these methods proceed by iteratively resolving the problem with different thetas and using that solution to inform the value of theta they will use next. And if I compare this with the method that I described yesterday, that Anna has been developing, then we see that when the noise level, so this is in the de Blering example from yesterday, we see that when the noise level is really low, then doing empirical base, which what we were doing yesterday, is definitely the right thing to do. You have a performance that is very close to Oracle, and the other two methods, the other Bayesian and Sugar, are suboptimal. If you go to a case where the noise level is very high, then marginalization is not that much worse than doing empirical base, and the main advantage is that you don't have to run MCMC algorithms. The computing times here are not something that I'm still 100% convinced that are right, in the sense that it's very tricky to decide the computing time in these experiments. It depends on how you set tolerance parameters within your optimization algorithm, what solver you use. Yeah, it's difficult to make a definite statement there. Also, one method is MCMC, the other one is just optimization. So computing times are very fishy. But we believe that marginalization with a good solver could be significantly faster than empirical base, and that empirical base will be more robust and give better results in general. And in any case, marginalization in our experiments is often better than Sugar, except in some cases that are very close to denoising. And yeah, Anna is working on a very exhaustive evaluation of this that is threatening her mental health by this point, but hopefully we'll finish in the next month or so and put that online. Okay, so I'll conclude by saying that I really think that it's a time where imaging sciences need a bit of a paradigm shift, not because what we have is not good, but because what we have is incomplete. There's a number of problems that we know how to solve really well, but there's also others we don't know how to solve pretty much at all, where things are really green. So yeah, this is what I have described as elephants in the room, and I hope that you will become interested in contributing to developing these other areas of imaging sciences that desperately need a bit of attention, and that you will start identifying open problems of your own, things that you realize we're not doing well, and where you could make a very valuable contribution to the community. Yesterday we talked about MCMC methods, and that vanilla MCMC methods, which were developed for other applications, do not necessarily work well for imaging, but that we can make good methods for imaging by combining tools from variational strategies, so optimization and MCMC sampling. And today we talked about strategies that bypass MCMC altogether, and they basically take advantage of specific properties, structural properties of the model that are quite general, like convexity or homogeneity for a regularizer. And in my next talk, that is going to start in a minute, I'll briefly, through a working example, illustrate a situation where Bayesian inference contributes in a different way. I'll show examples where optimization would not lead to any good solution. The model is far too complicated because the application really demands a complicated model. You have parameters that are discrete, parameters that are continuous, parameters that involve models that are not convex at all, that you can't even write down, and where Bayesian methods address that in a very natural way, whereas non-Bayesian methods would struggle. Thank you, and questions?
So, first of all, I'm very happy that you're willing to dedicate part of your life to finding a way to find the balance. So can you go back to this, call this MM scheme?
Yes.
So here you present it as an MM scheme, and I think in your statistical paper it was more like a fixed point type of iteration.
Yeah.
And does it make a difference? The first question, and the other thing is that you say that you see a single, do not really have local minima. But for example, if you apply this to an L1 regularized problem, if you start from a very high regularization, the first solution will be 0 and you will never change. So you see what I mean? If you regularize too much, you start from the theta 0 that you need to choose to find your first solution. will give you a zero solution, and then he will not.
So what we found is that, okay, so I observe a single minima when you have just one realization parameter. If we've not done a lot of tests where we put, I don't know, like one for each wavelet scale or things like that. In that case, because you have less samples per parameter, the central limit theorem that gives you this unicity will maybe be delayed and not kick in. If you start with a realization parameter that is too large and your solution is all zero, then what happens in my experiments is that the next value of theta that you choose is very low. And then you go from a very large value to a very small value, and then you start going up. Instead of, whereas here I just start from a slow and go up. So there's cases where it oscillates a bit and then it stabilizes.
But then this depends on alpha and beta, right?
So if you are in that scenario where where you don't have a lot of points, then maybe it will depend on alpha and beta. Because you forget alpha and beta as you have more data. Like, in general, when your posterior distribution combines prior knowledge and observed knowledge, so the data, and in general, under some regularity assumptions, as the number of data points goes to infinity, you forget the prior completely. And you get all your information from the likelihood. So in that case, alpha and beta are irrelevant. If you're a bit too far from that, then alpha and beta will make a difference. But what you can do is say, well, in my experiments, these values of alpha and beta work well. So for instance, alpha over beta is the expectation of theta. So you could set the expectation and the variance of theta a priori. Say, this is the range of values I want, and take it from there. But if that is not working, then you definitely want to use the empirical Bayes method that we will release soon, because this one doesn't depend at all on any hyper prior. There is no alpha and beta. And it doesn't average over all models. It goes for the best model. And when your model is misspecified, that is a much better strategy. It is more robust. Your data is capable of deciding which is the best model, but it's not capable of deciding if that best model is 10 times better than the other one or just 2 times better. So when you do the averaging over all the models, you don't give the right weights to the models. You don't promote sufficiently the best model.
You call technical Bayes is what people would call 2x2 maximum likelihood.
Exactly. Yeah. 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 Are there any other questions?